Today we'll continue with design of small water harvesting structures. Design criteria for dugout form pond. Rainfall analysis. Rainfall is one of the most important and critical hydrological input parameter for the design of form ponds. So rainfall analysis is the most important critical hydrological input. Design rainfall. It is defined as the total amount of rain during the cropping season at or above which the catchment area will provide sufficient runoff to satisfy the crop water requirements. So design rainfall is the total amount of the rainfall which is equal to or above to create runoff which satisfies the crop water requirements during the cropping period. If the actual rainfall in the cropping season is below the design rainfall, there will be moisture stress for crop. So if the design rainfall is less than, if the actual rainfall is less than the design rainfall, then there will be moisture stress for crops. That means we will have less water for the crops. If the actual rainfall exceeds the design rainfall, there will be surplus runoff which may cause damage to the structures. Rainfall runoff relationship. There are several methods to estimate runoff. However, SCS curve number is the most popular for the field engineers of soil and water conservation. So there is a method called SCS curve number which is being used for estimating the runoff for the farm ponds. It requires minimum data set of daily rainfall data, details of land use and its distribution, hydrologic groups of soil based on infiltration rate of the catchment area and antecedent moisture conditions of the watershed based on the previous 5-day consecutive total rainfall preceding the rainfall considered. So the data required for this method of estimation of the runoff are daily runoff data, details of the land use pattern and its distribution. There is the soil classification based on the infiltration rate and catchment area antecedent moisture condition, that is the moisture available immediately before 5 days of the rainfall 5 days of the rainfall on which day it is considered. So these are the data required for estimating the runoff. Curve number method. It estimates the direct runoff in terms of depth or rainfall excess storm wise. This method is based on the potential maximum retention S of the watershed, which is determined by wetness of the watershed, that is the antecedent moisture condition and physical characteristics of the watershed. So this method estimates the potential maximum retention of the watershed, which is determined by the wetness of the watershed, that is the antecedent moisture conditions. It is given by the formula Q equal to P minus IA bracket square divided by P minus A plus S, where Q is the runoff depth in millimeter, P is daily rainfall in millimeter, S is potential maximum retention of soil in millimeter, IA is initial abstraction in millimeter. That means there the losses or the infiltration. IA is related to S for different soil types. So the initial abstraction depends on the soil types. For black soils, IA equal to 0.2 S, and for red soils, IA equal to 0.3 S. Once the runoff depth Q is estimated, the volume in meter cube of the particular event can be calculated from the given equation, where runoff volume to be harvested equal to Q into AC divided by 1000 And there are some conversion factors. 1 hectare equal to 10,000 meter squares, or 1 acre equal to 47 meter square, and Q is a rough depth in millimeter, which is already assessed, and AC is the catchment area in meter square. Excavated farm ponds are of two types, namely square and rectangular. However, square pond is most commonly adopted, having less evaporation and seepage area compared to rectangular pond, and easy to construct. So there are two methods of construction, square and rectangular. Square is preferred because it will have less evaporation and seepage area. The storage capacity depends on purpose for which the pond is created, annual water yield, storage losses, area considering volume of silt anticipated. Dimensions. The dimensions are side slopes. The side slopes are decided by the angle of repose for the subsoil. Where the soils are very deep, the angle of repose for the deep black soils may also have to be considered. So the side slopes mainly depend on the angle of repose of the subsoil, and if it is deep or more than 90 centimeter, the angle of repose for the deep black soils may also have to be considered. The constant action of standing water may require relatively flatter side slopes to avoid slippage due to the saturation. So you may have to go for the flatter slopes to avoid the slippage due to saturation because of the standing water. Generally, side slopes of 1.5:1 would be sufficient for the morum obtained under the deep black soils in this tract. If the annual rainfall AR varies between 500 to 750 mm, the farm ponds with a capacity of 250 to 500 meter cube can be constructed. If the average annual rainfall is more than 750 mm, the farm ponds with capacity more than 500 meter cube can be planned, particularly in black soil regions without lining. You can see how the farm ponds are formed. You can see the contour layout, and you can see the drain which drains the water to the farm pond. You can see the elevation and sections of the plan and elevation and sections of the farm pond. In the plan you can see the inlet and outlets are provided for collecting and letting out the excess water, and also the excavated stone is used to form the earthen embankment around the pond, and the poles are provided to avoid the slippage of the earthen embankment. And the slide slopes will depend on the soil characteristics. One is to 1.5 is enough for if it is the morum base, or you may have to go for flatter slopes in BC soils, that is 1 is to 2.5. So these are the dimensions, how it is fixed depending on the slopes of depending on the slopes of the soil. Farm ponds constructed in red soil require lining for long storage of water in the structures. Lining of farm pond to control seepage and percolation losses would be helpful in supplemental irrigation at crop critical stages, livestock rearing, and domestic water supply. If the farm ponds are constructed in the red soils, they require the lining to store the water for a longer period and to supplement the water for irrigation at crop critical stages, and for the requirements of livestock and domestic uses. Lining is required in farm pond to control seepage from the wetted surface area. So lining is required for the sites where the water seeps through the wetted surface area. and the bottom. Seepage losses are predominant in case of light textured soils where sand percentile is more as compared to clay and silt particles. So seepage losses are more where the soil consists of more sand percentage rather than the clay and silt particles. The locally available material such as bricks and stones are used for hard surface lining of farm ponds, or the linings may also be constructed by using cement, concrete and mortar. However, with the advent of new improved technology in the material science, the uses of polyethylene sheets have become popular among the farmers. It is required to select a proper thickness of the film for longer life, but the expected life for such film is 5 to 10 years. So, with the invention of new materials, now the farmers are using polyethylene sheets as a lining material, and it requires a proper selection of the thickness, and the life expected for such linings is 5 to 10 years. Presently, the HDP films of 500 micron or cross layers reinforced sapolene with 300 to 350 GSM are commonly used for lining of farm ponds. The areas around the farm pond could also be developed for growing horticulture and vegetable crops, which would further make the system more viable. So the area around the farm pond can be used for growing horticulture and vegetable crops. Thus, water harvesting and runoff recycling helps to stabilize and support a large proportion of agriculture in semi-arid tropics. It further brings an awareness in the farmers on the benefit of conserving the twin natural resources like soil and rainwater. Harvesting surplus runoff in dugout ponds and recycling the same for providing supplemental irrigation to kharif crops or pre-sowing irrigation to rabi crops has proved to be the most successful technologies for adoption. So harvesting the surplus runoff in using a dugout pond, the stored water can be used as a supplement to the kharif crops. So that means during kharif season, when there is dry spells, this water can be used to supplement the requirement of the kharif crops, and also the stored water can be used for pre-sowing activity of the rabi crops. Although the fall pond technology is well known in the country, its adoption has been quite low due to number of constraints like high initial cost, short life of the lining materials, lack of suitable lifting systems, and above all, low awareness among the farmers about its utility and cost benefit analysis. So, fall pond technology is a well known technology. Still, we are not using its adoption. It is not using, we are not using, or we are not adopting to its full potential because of the constraints like high initial cost or the short life of the lining materials or lack of the suitable lifting system and the low awareness among the farmers. We will go through design of a percolation tank. Percolation tank is an artificial reservoir constructed across stream, submerging a land area with adequate permeability to facilitate sufficient percolation to collect the surface water runoff and allow it to percolate within the permeable land. So, percolation tank is a structure created to store the water or store the runoff, and the soil characteristics are so that it is having sufficient permeability to allow the water to percolate and to enrich the groundwater. This is one of the effective methods of refilling the groundwater table, also known as groundwater recharge. The ideal size of the percolation tank must be governed by its capacity of strata in the tank bed. Usually, percolation tanks are designed for storage capacity of zero point 0.1 to zero point 0.5 million cubic meter, and a ponded water column should be generally between 3 to 4.5 meter. The ideal sizes depends on the volume to be collected, the quantity of the water to be collected. Usually they are designed for a capacity of zero point 0.1 to zero point 0.5 million cubic meter, and the usually the depth provided are 3 to 4.5 meter. And the general guidelines in the design are percolation tank should normally be constructed in a terrain with highly fractured and weathered rock for speedy recharge. Too high permeability may result in the percolated water escaping in the downstream as a regenerated surface flow, hence it will defeat the purpose of water conservation. So the percolation tanks should normally constructed on the strata where it is highly fractured and weathered rock for the speedy recharge, but it should not be too permeable. If it is too permeable, then the water will escape to the downstream as a regenerated surface flow, which will defeat the purpose of the conservation. The aquifer to be recharged should have sufficient thickness, about 3 meter, of permeable water zone to accommodate recharge. So the aquifer should be such that it should have a thickness of about 3 meter as a water zone or the unsaturated zone, which can accommodate the recharge. The benefited area must have sufficient number of wells, hand pumps, etc. So the area where the percolation tanks is located should be having sufficient number of wells and hand pumps around it, because that the stored water or the infiltrated water can be used through these wells and hand pumps. It is advisable and benefiting to have the percolation tank in an area of good average catchment. A long-term evaluation of the pattern of the rainfall for the benefited area must be studied so that the percolation tank gets filled up fully during monsoon. To minimize the silting at the bottom of the tank, soils in the catchment area should preferably be of light sandy type. So we should analyze the rainfall pattern so that the percolation tank gets filled up fully during the monsoon, and also the catchment area what we choose should be of light sandy type to avoid the silting of the percolation tank. Except for outlets provided for surface irrigation and the depth of cut and the depth of the cutoff trench, there is not much difference in the construction between a percolation tank and a minor irrigation tank. So there are similarity of similarity between the percolation tank and the minor irrigation tank for the construction purpose, except that the outlets are provided for the minor irrigation tank and they are not provided for the percolation tank, and also there is a difference in the depth of the cutoff trenches. India is a country of diverse climates and types of land conditions. The geographic condition of the India affects the use of percolation tanks, because India is having a diverse climatic and land conditions. The the use of the percolation tanks affects these geographic conditions. Capacity of the percolation tank has to be calculated on the basis of the rainfall and catchment area of the tank. Also, the weir length has to be calculated. The procedure adopted are as follows. Select the site for the percolation tank. From the topo sheet, find out the correct catchment area of the watershed at the locations. So you identify the location of your percolation tank, and from the topo sheets arrive at the catchment area of that particular watershed. Compute catchment yield from rainfall and runoff coefficient or Strange's table. So you can calculate the catchment yield using the runoff coefficient of the tables available. Make suitable assumptions such as number of fillings per year 2. So you have to make some assumptions that you are going to fill up the tank twice in a year, and utilization of the yield per filling. and also you have to assume the utilization of the yield per filling. So in the first filling, if you may not use the stored water to its full capacity or the full availability. So for the second filling, we have to consider the utility of the yield in the first storage also. So you have to your capacity has to be based on utilization of yield per filling also. Compute capacity of the percolation tank based on these factors. Then you develop the stage capacity curve or table. Stage capacity curve is so depth of the water column and the capacity of the water stored in that particular height or the depth of the water. Draw the contour lines at every 50 centimeter interval between the bed level and the highest ground level at the site. So you have to prepare a contour map with a 50 centimeter interval right from the bed of the nala to the banks or the highest point of the ground level. From these contour lines, the capacity of the tank at 0.5 meter, 1 meter, 1.5 meter, 2 meter, etc. height above the bed level is calculated. Make allowances for freeboard and settlement. So you have to make the provision for the freeboard and the settlement. Freeboard is usually uh, make provision of 1.5 HW, where HW is the height of the wave. So when you store the water, there will be generation of some waves, and depending on that wave height, you have to decide for the freeboard. Wave height in meter is usually calculated as 0.014 into dm to the power 0.5 or square root of the dm. That where dm is the fetch length, the longest exposed water surface of the reservoir in meter. So when you store the water, you have to consider the longest exposed water surface in length in meters. So our formula equals the height of the wave. Settlement depends upon the type of fill material and the method and speed of construction. Varies from 10% of the design height for hand compacted to 5% for machine compacted road at optimum moisture fill. So we have to make the settlement provisions. When you construct an embankment, there is a chance that there are the chances that it gets settled, and the settlement depends upon the type of construction. If it is labor oriented construction, then we have to make a provision of 10% of the design height as a settlement for settlement purpose, or if it is machine compacted, we have to go for 5%. That means you have to construct the height an extra 10 or 5% depending on the type of construction procedure used. Compute top width of the embankment. The top width of the embankment W is equal to h bar 5 plus 1.5, that is h is the height of embankment in meter. Compute length of embankment. Length of the embankment is the distance between the 2 points where the height intersects the contour having same elevation. Based upon the type of material, assign suitable side slopes for embankments. So depending on the soil type, you have to select the slopes of the embankment. The following table gives the different slopes to be adopted for upstream and downstream for different class of material. Homogeneous, well graded, it is 2.5 is to 1 and 2 is to 1. Homogeneous coarse silt, it is 3 is to 1 and 2.5 is to 1 on downstream. Homogeneous silty clay, where the height is less than 15 meter, 2.5 is to 1, 2 is to 1, and height more than 15 meters. So you have to adopt 3 is to 1 and 2.5 is to 1. Sand or sand and gravel with central clay core. We have to go for 3:1 and 2.5:1. Compute peak discharge depending upon the catchment area and type of corresponding data available. So you can use the rational method or some empirical formulas. The rational method, the formula is Q equal to CIA by 36, where Q is the peak discharge in meter cube per second, C is the runoff coefficient, I is the intensity of rainfall for duration equal to the time of concentration of the watersheds in centimeter per hour, A is the catchment area in the watershed in hectares, and empirical formula, Dickens formula, Q equal to C into A to the power 3 by 4, where Q is peak discharge in meter cube per second, A is catchment area in kilometer square, and C a constant which is termed as for North India it is about 11.5, Central India 14 to 19.5, and Western India C equal to 20 to 25. The formula is generally useful for catchments of North India. An average value of C equal to 11.5 is generally used, and it is increased for hilly catchments and vice versa. And another empirical formula being used is Rice formula, where Q equal to C into A to the power 2 by 3, where Q equal to peak discharge in meter cube per second, catchment area in kilometer square, C a constant for areas with 80 km from the coast, C equal to 6.8, areas within 80 to 2400 km from the coast, C equal to 8.8, areas near hills, C equal to 10.1, actual observed values C are up to 40. The formula is applicable to catchments in South India. The average value of C to be used is 6.8, with less value for flat catchments and more for hilly catchments. Compute the length of spillway using peak discharge. For small tanks, the height of the flow over weir is taken between zero point 0.3 to zero point 0.6 meter, and this level is known as maximum water level. So we have to fix up the spillway length and height. Usually the height of the spillway is kept around 0.3 meter to 0.6 meter for small tanks. To decide the length of the surplus weir, we have to use the formula Q equal to C into L into S to the power 3 by 2. That means L equal to Q divided by C into S to the power 3 by 2, where C is a constant which is equal to 1.67 for broad crested weirs. L is length of weir in meter. H is flow height over the weir in meter. Compute width of horizontal floor. The width of horizontal floor of masonry weirs with vertical drop from the foot of the drop wall to the downstream edge of the floor should not be less than 2 into D plus H, where D is the height of the drop wall and H is the maximum head of water over the wall. So we have to decide the width of the horizontal floor, which is to be provided on the downstream, and it depends on the D, which is the height of the drop wall, and H, the maximum head of the water over the wall. The rough stone apron forming a talus below the last wall may be taken from 2.5 D plus H to 5 D plus H, depending upon the nature of the soil and the velocity. So I have to provide a rough stone apron with a for a length of 2.5 D plus H to 5 times D plus H, depending on the nature of the soil and the velocity of the flow in that waste weir or the spillway. Then check the stability of the structure by locating the saturation line on the base. Then we have to check the stability of the structure by locating the saturation line on the base. So there are the method for checking the stability of the gravity structure. So to use that method to check the stability of the structure. And this is how the section of the percolation tank embankment is like. So we see this is the casing material which you call as the casing material of the embankment, which is available locally available in that area, and you have to provide an impervious core at the center, and this is the key trench which is provided. Then we have got the stone pitching over the filter media. Then we have got the downstream slope, usually which is protected by turfing. So this is the section how it looks. So there is a solid example of the earthen embankment for percolation tank. Design an earthen embankment using the following data: catchment area 21 hectare, intensity of rainfall 17 centimeter per hour, RL of the ground surface 100 meter, RL of the HFL 103 meter, runoff coefficient C equal to 0.3, soil type is sandy loam, slope of saturation line is 4:1, assume a fetch of 500 meter. Hence compute height of the water up to HFL, compute height of the waves, compute freeboard, compute allowances for settlement, assign upstream and downstream slopes from table, compute peak discharge, compute the length of the spillway, assumed head over spillway crest is assuming it as 0.3 meter, compute width of the horizontal floor, locate the saturation line for checking the stability. Solution: height of the water up to HFL is, that is 103 minus 100 is 3 meter. Height of the waves SW is given by this formula, and it works out to be 0.31 meter. Freeboard, that is F equal to 1.5 into height of the wave, works out to 0.46 meter. Height of the embankment, total height of the embankment including the freeboard is 3.46 meter. So considering the allowance for consolidation or settlement, taking it as 5% using the machinery construction, then it is about 0.17 meter. The total height of the embankment to be constructed including freeboard is 3.63 meter. Top width of the embankment will be h by 5 plus 1.5, which occurs to be 2.3 meter. Using the respective table, adopt the following side slopes of embankment for sandy loam. Our upstream slope is 3:1 and downstream is 2.5:1. Peak discharge is calculated using the rational method, which works out to be 2.975 meter cube per second. Length of the spillway using that formula, L equal to Q by C into S to the power 3 by 2, it works out to be 10.84 meter. Width of the horizontal masonry floor, W1 is 2 into D plus H, which works out to 6.6 meter. Width of the rough stone talus is about 13.2 meter using the formula, and it is taken as 4 into D plus H. So actual length required for saturation line to be in the base embankment is 21 meter. So length available for saturation line to be in the base of the embankment is 22.2 meter. So hence the structure is safe. The saturation line meets the base of embankment, therefore the section is stable. So you can see the details of the section are as below. Okay, thank you.